So today we're doing a thermodynamics question to keep myself entertained and motivated. So a vessel of volume V equals 30 liters contains an ideal gas at the temperature 0 degrees C. After a portion of the gas has been let out, the pressure in the vessel decreased by delta P equals 0.78 atm and the temperature remaining constant. Find the mass of the released gas. Then we have the gas density under the normal conditions. Okay, so whenever we see volume, pressure, and temperature, we know we're going to use the ideal gas law, which is PV equals NKT. So first of all, I think it's important to actually label what all of these things mean. So P is, of course, pressure, and here we're measuring it in atm. V is the volume the gas is constrained to. So this is important because it's the volume of the container, essentially. So whatever the gas is occupying, the volume of that container. So in this problem, it's in liters. And we also have N is the number of molecules. We have K is a constant, and T is the temperature, of course, which in this problem we said was also constant. So it's isothermal. So we'll just label it as constant. Okay. So first, let's actually draw out what is happening. So we have an initial container. I'm just gonna label it as initial. And we have gas in it. Okay, so those are molecules of gas. And we have, let's say, a little valve here that's releasing some of the gas into a different container, right? So a portion of the gas is being let out. So let's just say that over here, it's just being let out into some other volume. So here, I'm gonna label this as removed gas. Okay, and then eventually we're gonna have a final where we have less molecules than we had in the initial because we released some of them, right? We removed some of those molecules. Okay, so what I like doing is making a table. So we'll just label the P, V, and N. So N is important, right? Because we don't have the same number of molecules in initial as we do in final because we removed some of those molecules. Okay, so I'll just make a table like that. So in the initial container, let's just say our pressure was PI. Okay. Now in our final, we changed it by delta P, right? As the problem told us, the pressure changed by delta P. So the final, we'll just say it's PI plus delta P. Now for the removed gas, so if we're removing the gas into this container, let's say that we're removing the gas until it reaches an atmospheric pressure. My God. Until it reaches an atmospheric pressure. So until it reaches P naught. So P naught will be 1 atm. So let's just say the volume of this bag increases until the pressure inside it reaches 1 atm. So I'll just say this volume is some random volume V1. And the reason we want to do that is because we were given the conditions under normal conditions, right? We were given the density under normal conditions. So if we're releasing our gas into a container at which the gas will be at 1 atm, we can use these normal conditions because remember, the temperature is constant, right? Our temperature was at 0 degrees Celsius, and at normal conditions, P0 is 1 atm, T is 0 degrees Celsius, and we already have those conditions. So then we can say that volume is m over rho. M is what we're trying to find, right? And rho was given, right? And the number of molecules that are in this bag of removed gas, let's just say that's delta N, because it's different from the initial number of molecules, which we'll just say is N initial. And then the initial volume we know, it's V0. Remember, this is the volume that the gas is constrained to, so it's the volume of the container. So I'll label that as well. V0 is 30 liters. And our final container will also have a volume of V0, right? Because the container is not changing at all. Okay. And then our final number of molecules, well, it's just our initial number of molecules plus whatever changed. Okay, so now we're ready to set up our equations of state. So I'm just going to write it out for every section. So for initial, right, we have P V equals N KT. For removed gas, we have P naught V1, which I'll just write M over rho equals delta N KT. And then for final, we have Pi plus delta P. V naught equals Ni plus delta N KT. Okay. So note how all equations have KT. Remember that K is a constant, T is a constant, right? So we can actually just ignore those. I'm just going to cross them out because they're really not important. We really don't need these. Okay, now let's try solving the equation. So essentially, what equation do we want to solve? Well, we're solving for m, right? That's what we wanted. We wanted m. So let's start with this equation because this is the one that has m. So m equals delta N rho over P naught, right? Now, what's delta N? Well, we see delta N in this equation. So let's go and solve for this equation. So Pi plus delta P V naught minus Ni equals delta N, right? If we just move this to the other side. And then what's Ni? Well, we do know Ni because that was our first equation. So if we expand everything, right, and now I'm just plugging in Ni for what we had here, which was Pi V0. Then we actually get that Pi V0 cancels out. And delta N is delta P V0. So let's substitute that into here. So delta N is delta P V0 rho over P0. Right, so this is M equals, and if you check the answer at the back of the book, it was exactly that. So that's your answer. And if you wanted to plug in the numbers, so what's delta P? Delta P was 0.78 ATM. V naught was 30 liters. Rho was 1.3 G per liter, and this was all divided by 1 ATM. So atmosphere cancels out, L cancels out. If you put this in a calculator, it's 30.42 grams. In the book, they just have it as 30 grams. Okay, so that's 2.1. Thanks for watching.